How's it going, everyone? Hope we're all doing well. Next up lecture here is on adding and subtracting, and we're going to also talk about multiplying and dividing. So now we've got a very good baseline set of understanding when it comes to significant figures. Next comes some of our basic operations and how we go about making sure that we are using the correct number of significant figures whenever we have a mathematical operation like adding and subtracting, and then like dividing and multiplication as well. So we're going to talk about those two in just a minute. But here is the set of rules to follow whenever you are adding and or subtracting numbers. So when adding or subtracting, round to the same number of decimal places as the measurement with the fewest number of decimal places. Your answer should then reflect that fewest number of decimal places itself. Okay, so noticing that there are 3 different places on this slide alone where I have bolded and underlined the words decimal places. Adding and subtracting only ever follow a rule for decimal places. So whenever you add or subtract multiple, 2 or more different measurements, you're always following decimal places and not significant figures. We'll save significant figures for the next slide. But whenever you are adding and subtracting, we are always making sure that we round to the number of decimal places as the measurement with the fewest number of decimal places. And again, when we talk in class up next, when I see you next, we're going to be doing several examples of this, so don't fret too much. Okay. Again, so whichever number in your set of adding and subtracting has the fewest number. Let's say you've got 3 numbers, 2 with 2 decimal places and 1 with 1 decimal place. Well, the number with 1 decimal place is what you should be rounding your answer, your final answer to. Okay. Skipping ahead a little bit here over to multiplying and dividing. Now, this is where things change a little bit, right? Hopefully you notice that on the slide. Now, when multiplying or dividing, we are rounding to the same number of significant figures this time as the measurement with the fewest number of significant figures. So again, it's a little bit different here, right? Because previously with adding and subtracting, which we will look back up to in a second here, okay, decimal places was the case, right? Whenever we were adding and subtracting things, we were always looking at decimal places and the fewest number of decimal places, and that's what your answer reflects. Now with multiplying and dividing, we're back to sig figs, okay? So that's kind of why we spent the time last class really hammering home what is a digit, what is a decimal place, and how they play into how our calculations should end up looking like. Now with multiplying and dividing, again, we were looking at the lowest number of significant figures. So if you're multiplying 3 numbers together, your first number has 3 sig figs, your second number has 4, your third number has 5 sig figs. Well, the lowest number of significant figures is 3, which means you need to make sure that your answer is also in the lowest number of sig figs, which in this case, again, is 3, right? And again, in class, we'll do more examples, or we will do a few examples of showing this off, okay? But once again, skipping ahead a little bit is one of the last calculations and is another formula that you guys are given here. So it's called the percent error formula. You guys actually would have been doing this on your very first lab write-up. Some of you guys already handed it in. Some of you guys are going to be handing it in very soon. But the percent error formula provides information on how far a measured or calculated value is from an accepted value, right? So there's a very big difference between what the measured value is and what the accepted value is. Now let's think about it this way, all right? The measured value is what you yourself literally measured in the lab experiment, right? So in our lab experiment, you guys did lab number 1 and lab number 2. The measured value comes exactly from your calculations, whereas the accepted value is what is technically accepted by the scientific community as actual fact. So let me give you another example of that. Right, let's say you've got the definition of some word, right? The accepted value or the accepted definition of that word is when you go into the dictionary, like the Merriam-Webster dictionary, and you look up the definition of that word, right? That's what everybody in the world would refer to as the accepted definition or accepted value of that word. The measured value or the measured version of your word is your interpretation of that word, right? So you take that same word you looked up in the dictionary, right? And you come up with your own definition of that word. That's the measured value. So whatever you yourself did and found in the lab environment, that's the measured value, your calculations. The accepted value is opposite of that. Okay, that's what the scientific community references as a whole. to make sure we're all on the same page. Okay, so you use those two different things, and you will pump out a percent error, right? So the lower that number, the lower that percentage, the better off you are, right? If you have a really, really low percent error, that means you were super close to the accepted value, and that's really, really good. The higher that percent error is, though, the farther away from the accepted value is and the less accurate you are. Skipping ahead a little bit again into something called scientific notation. We're going to do a couple examples of this in class whenever I see you next. But scientific notation is really important because we're going to utilize it a handful of times throughout the school year. But there's two main things I want to be able to focus on when it comes to scientific notation. First and foremost is converting into scientific notation, taking a standard number, right? So there's standard notation and scientific notation. So if you have some number in standard notation, we want to first be able to learn how to convert from standard notation into scientific notation. That's the first chunk here. The second chunk is to do the exact opposite. Take a number in scientific notation and convert it into standard notation. So starting out, to convert into scientific notation, if a number is greater than 1, you move the decimal place to the left until only one digit is to the left of the decimal point. The number of places you moved is, the number of places you move that decimal point becomes the positive exponent. Now, on the other hand, if the number is less than 1, we have to move the decimal place to the right until only one digit is to the left of the decimal point. And now, instead of that becoming a positive exponent, that number of decimal places, the number of decimal places you move is going to end up being your negative exponent. So a little bit of a difference there. And again, more often than not, when it comes to stuff like this, me explaining it is not always the best way to learn about this. So this is just your first exposure to it in this video. But again, we will hammer it out a bunch when I see you guys in class next. Now, to convert out of scientific notation, it kind of follows the same steps that we just read, but in reverse. So if you see a positive exponent, you utilize that to move decimal places to the right, the same number as the exponent, and then the number of and then make sure to place zeros as placeholders to get the final answer. If that negative exponent is present, you're going to move the decimal place to the left the same number of times as the exponent present, and then, of course, again, placing zeros as placeholders to get the final number. Okay. Now, lastly, whenever it comes to using scientific notation, when a number is expressed in scientific notation, and you guys actually would have referenced that and saw that in your most recent set of classwork whenever we finished sig figs, you actually would have saw a number in scientific notation. But the number of digits present in scientific notation ends up actually being your number of sig figs as well, right? So if you see a number in scientific notation, right, that base number, like let's say 6.02, 6.02, that's 3 digits, also 3 sig figs. Okay, so no matter how many digits you have, if a number is in scientific notation, that's also the number of sig figs that it currently has too. That's it for today's video. Thank you so much, and make sure you get your two or more discussion board posts in to Schoology. Yeah, thanks. See you in the next one.